So welcome to the 8th class of data analytics. Okay, so this is the second half of the course, which is probably a bit more fun and more engaging than the first half. The first half, we had to give you the necessary foundation. So if you recall, you have the introduction, which is really what the concept of data is all about, what the concept of analytics is all about, right? And then because we are using Mathematica as high level, language for doing data analytics. As with the textbook, we have this kind of like partitioning, right, into three modes, right? Three sort of like units, so to speak, right? So one is the interactive, visualization, okay? And once again, this is important in three stages, right? First of all, it's a final product. So you visualize and you get the insight right away, right? So that's sort of like end product. Second, it's for you as data scientists to get to sort of like know about the data, right? So that's for you to familiarize with the data itself. And then finally, once you've done your analytics, you present your finding to your client, to your market, to your shareholder, your stakeholder, whatsoever, okay? So this thing will be used for the next two things as well, right? Because the next two things is about the tools and the analysis. So we have probabilistic modeling, okay? And now we begin with machine learning, right? Machine learning. So this is a foundation for you to be able to understand this class. And these are the three modules, okay, the content of the class. Now, this one I didn't spend a lot of time on simply because a lot of you would have had probability and statistics, maybe in high school or maybe in first year. But the point of it is, I give you a more intuitive tools, more practical tools, top level of trying to find, you know, the fit, the distribution, and so forth, right? And now we are actually going to jump to the machine learning part proper. And then finally, you have some kind of term project. Okay, so this is kind of like a separation between the first and the second half of the course, right? So everybody's on the same page. Now, let me go back to what I usually often say, and I keep saying this to you. What is data analytics all about? It's usually about two things. This and this, right? This is sort of like the two things we're talking about, okay? So where are the X's? Where are the data? What does it look like? What are we dealing with? Okay. And the other one is the information that's contained in X about Y. Okay. And presumably in terms of practical application, Y is what you're interested in, and X is what you have a handle on. Okay. So this is giving you again, predictive capability, right? Because the idea is you're not predicting X necessarily, but you sort of like given X and then you predict Y. Okay, so if X is today and Y is tomorrow, then you have a way of predicting the future, so to speak. So that's basically it, right? Now, let me just stress that point by saying, in terms of visualization, what is the main method? Basically, the go-to method. You get a data set, okay? The data set. What do you do to get an idea of where is the data point? Where are the data points? Well, it's the histogram, right? So in terms of visualization, forget about the interactive part, okay? So you do this, you do histogram, and that's where things are, right? Right? And if you're talking about this relationship between X and Y, okay? By the way, this is also the name of the built-in function that you can call, right? So what is the visualization of how X and Y are related? Well, obviously, that's the scatter plot, right? Right? Yeah. But I'm not going to write scatter plot because I'm going to use the word list plot because that's the function we use. Right? Because in Wolfram Mathematica, list is the most basic form, right? And if you're plotting a list of coordinate, list of X and Y, that's basically plotting the scatter plot X and Y, right? So this would be a more like an English term. This is the name of the function. So maybe I'll put this like this. Okay. And that would look like just a whole bunch of points. Okay. All right. So again, in terms of visualization, you do it at the beginning of your data science project so you get an idea of what your data is like. I'll give you an example. For example, if you do this and it shows a pattern that's nonlinear, you'd be silly to draw like a linear regression to it, right? So that's a sort of insight to help you build the model. But if the objective is, well, you can see right away, you don't even need to do any kind of fitting. Just say, oh, okay, that's the relationship, right? And again, what's the most, what is the go-to example, for example? What's the go-to example that I use? Well, instead of scatter plot, you can do also a time series plot, right? Where this is not any X, but this is time, right? And then Y is something like, say, global temperature or part per million of carbon dioxide, right? And then you get something like this, right? Again, you can fit sophisticated mathematical function to it, but do you really need that? No, because you already done the, you get your message across. You say, okay, this is what happened when we got the industrialization. This is after World War II, you know, and the curve just goes up like that. Crazy, right? So basically, when we started to dig out coal in the Victorian Industrial Revolution, and then when we start to use petroleum or petrochemical as a main source of energy, right? Okay, so again, we do this. So this would be the picture for visualization, right? So remember, these are the key. I mean, if you don't remember anything, just keep in mind. Okay, I'm talking about visualization. Where are things? Go to histogram, right? Go to histogram. And you have histogram in 1 dimension, 2 dimension, whatnot. Where are things? If you know X, can you tell Y? Well, that's where list plot comes into play, right? Okay. So that would be the visualization part. Now, here it's kind of like, you kind of use them both equally. Now let's go to probability in statistics, okay? Probability in statistics. Again, I have this. And then I have this. How do you answer this? Well, you can think of it as 2 era. The era before fax machine, when you have a telegram, how do you tell your friend where the data are? How tall are the people in the new country that you're visiting, right? How would you do that? Well, you would give it the 4 main statistic, right? Moments, basically from the mean and so forth, right? But so I'm just going to call it summarizing statistic. So you have central tendency, you have kind of dispersion, you have some kind of skewness, and you know, that's all. So these are the numbers, right? These are things you can communicate with a telegram and not with a fax machine, right? Well, with a fax machine, you could have faxed the whole picture, right? With a fax machine, you can fax the whole picture of the histogram, okay? Now imagine you, again, you're still working in the world of a telegram. You can't fax the whole picture of a histogram. However, if you said it looks like normally distributed with mean equal to 7, standard deviation is equal to 2, okay? So now instead of using reporting just the mean and standard deviation, you add another word and say it looks normally distributed. Okay, so 3 words. Send it to the telegram, and the other person at the other end can do this by himself. So that's mean, right? Okay, so that's a way of telegraphing where are the data. Okay, you're not sending this picture, you're sending the name of this shape, you're sending the value of mu, and you're sending the value of sigma estimate. Okay, and that person can draw it himself. So in his mind, he's gonna say, so maybe if I take a histogram from the data, original data probably looks like that, right? He can sort of like work backward. Okay, the reason you told him that it's normal distribution is probably because it has this kind of shape. The histogram looks like this shape, right? Now, of course, the most modern version would be something like, well, the reason you tell your friend it's normal distribution is because you put this data in Mathematica and you use the word function find distribution, and then it returns normal distribution, which means 7, standard deviation equal to 2. Okay, but same thing. Okay, you don't need picture now. But the idea is once you got this, you got a mathematical description. Okay. And then a lot of statistic is about testing. And, you know, I really skip a whole bunch of statistical testing because it's very much standard on statistics, like confidence interval, hypothesis testing and whatnot. Now, I want to say, what about statistical world's way of doing X and Y? Well, that's the regression equation, right? That's kind of like drawing this kind of this. So Y is equal to A plus BX plus some kind of noise. And you are trying to find what this is and what that is. Again, you could do this at your end, communicate it with a telegram. The telegram say it's a linear equation with coefficient equal to A. The intercept equal to A, coefficient equal to B, and standard deviation equal to C. Okay, so now you send 4 words. Okay, so what's the intercept? What's the slope? And what is this? And what's the model? Right? Okay. So think of statistics as doing a lot more sophisticated way of presenting this mathematically. Yeah, I kind of made it a sort of like a funny anecdote that the reason you need to do all this mathematics is because you can't send a fax, right? So you have to summarize everything with mathematical function and all that. I'm just being saying that in jest, but you know that's not too far from the truth. That's not far from truth actually, because if you think about it, computer graphic is 300 years after regression equation, right? So all this again is trying to ask where are the data, but instead of showing it with the histogram, you show it with the name of the best fit distribution with the best fit parameter. Okay, Now, if it's another shape, you don't say it's normal, you can say it's gamma, you can say it's beta, whatever, okay? Likewise, how does X lead to Y? In visualization, you just say X and Y. How do they look together? Okay. If X is high, Y is high, then, you know, sort of like X, higher Y kind of thing. You just show the picture. That's visualization. But if you want to visualize with mathematical description, right? You just say, imagine that X and Y are related with the linear equation with some noise. Okay. So then you have this. So instead of having the mean here and standard deviation, the mean is a function of X. That's all, right? Now, I did say that, you know, in visualization, the top question and the bottom question are sort of like used sort of like evenly in application. With probabilistic model, okay, you would see, and, you know, go to ask your friend in statistics department, a statistic textbook would have something like 90% of this and 10% of that. Okay, 90% of the above, 10% of the bottom. In other words, regression is almost like the last class of the semester. For a very good reason. For a very good reason. You have a lot of mathematical sophistication that think up all this distribution. But this thing is kind of like empirical thing. And to be honest, it's not that successful. And in the future, I can imagine, now that we've got machine learning, now that you got machine learning, this thing might, you know, in the next year's statistics lecture, maybe this thing will go up to 95%, this thing will go down to 5%, because this thing is not usually done with linear regression anymore. Now it's done with neural network, now it's done with machine learning algorithm stuff, okay? So it's even, but it's good, but it should not go to zero, because the way of thinking Y as a function of X plus noise, that is so fundamental. I still have that thinking. I still have that thinking to this day, even though I've been working with machine learning and AI for a lot longer than I work with traditional statistics, right? I still have this thinking, right? Which part is deterministic as a function of some variable I can account for, and which part is noise. So this linear regression thinking is so important, not in application, but as a way of framing your thinking about how X and Y relate to one another. Okay. By the way, just to give you another thing, this thing, right? The phrase for it is the deterministic part. This is the random or noisy part, right? Sometime in some application, it's not so much deterministic versus random as opposed to endogenous versus exogenous. Endogenous is in your model because you can measure it, you can control it. The other thing is maybe, you know, deterministic too, but because it's not in your control, you see what I mean, right? So for example, how smart you are depends on how many hours you spend here, okay? Plus the coefficient, another coefficient multiplied by the number of hours you spend reading on your own, right? But if I'm going to do some kind of study on my student, I only know how long you're spending with me, okay? So the time you spend with me is endogenous variable, okay? So yeah, maybe the equation of what makes you smart is the number of hours you spend reading, but because I have no idea, I would have to treat it as random, okay? And to an extent that you guys have different reading hours, as far as I'm concerned, it's random. This guy reads on his own 5 hours. This one reads 1 hour, you know, completely out of my control. So sometimes it's not deterministic versus non-deterministic as opposed to part of my model and not part of my model, accounted for and not accounted for. Okay, that's just a comment to elaborate. Okay, now, okay, so now we come to this half of the class. Again, we're gonna do this. So once again, we're going to do this thing. Where are the x's? Right? And then if I knew x, can I predict y? Okay. All right. Now I'm going to give the game away and say that this thing will be answered by this thing called unsupervised learning, machine learning. This thing will be given by supervised machine learning. Okay. And you take out your textbook. Where is the unsupervised learning come first? Okay. And supervised learning comes the chapter after. Okay. So it's chapter 5 and 6, right? Chapter 5 and chapter 6. Okay. Now, let's talk about, I guess, breakdown. I said before that, in visualization, where are things, i.e. histogram, versus how X and Y relate to one another, or scatter plot or list plot, kind of like 50-50, right? In probability and statistics, where are the data, which is an analysis of distribution, right? And parametric estimation, hypothesis testing, all kind of stuff. That's kind of like 80-90%. And then and then regression equation is kind of like 10-15%. Okay, that's in your class. Now, how about this? Well, I would actually say for machine learning, in the public's mind, this is the majority. So I would put this thing as 70%. Okay, now, don't quote on this. This is not something that you can, I'm going to test you on. It's not a fact. It's not. But this is basically some kind of priority or majority, and this is kind of like less so. Why do I need to tell you this first? Because when we go to the world of AI, you would see that all of this will correspond to what we call predictive AI. And predictive, in a way, the reason you call it predictive AI is because basically you do this. You do this a lot. Yeah? X and then Y. Given X, what's Y? Predict Y from X. Okay? So the whole world that I'm going to give an introduction to, of AI being separated into generative AI and predictive AI. Predictive AI is based on ground truth, but I would consider this also part of that kind of world where you're working on ground truth, but you're not predicting anything. You're just trying to find insight. Okay, so again, 3 modules of learning. Each of them is a representation of what we do in data analytics. And data analytics is all about asking 2 kind of questions. Where are X's? Okay, where are they? Where are they? Where are the people? How tall are they? How short are they? Okay, right? Study the population. And then the other thing is, can I learn from the past example, past matched pair of X and Y, so that in the future, if somebody whisper in my ear what X is, I can predict Y with some degree of predictability, reliability, okay? And that gives me an edge. That gives me an edge. So the edge is not X first. The edge is everybody know X. But only you can make a good prediction of Y. Okay, that's like you have 2 radio stations who are competing on who's going to be the most accurate predictor of rain tomorrow. Okay, well, both radio station knows the state of the atmospheric reading today, but one of them has got an advanced model, can say tomorrow will rain with probability 60%. Okay, whereas the other one would get it wrong most of the time. So the first radio station wins basically, right? Okay, he doesn't win because he knows more about X. He wins because knowing the same X as everybody does, I can make a better Y. Now, I'm going to put a big bracket to it. That is not always true. I mean, that's only half the story. Because in real life, just because X is available to everybody, you may not know. For example, let's say that there's a factor about X that has to do with something else, pollen count, okay? Something else, pollen count, okay? But maybe that's not a good example. Let's say everybody has the same access to the same X, but one station doesn't know that one of the X you should consider is barometric pressure, okay? The other station takes that into account. So even though in theory you have access to the same X, right? The smarter guy would pick the right X and maybe have a larger class. And this is where corporation, marketing, that's the whole point of mining your behavior. Okay. So in other words, when I said that you beat the other guy given the same X, yes, your model is better. But also, you also have a larger class of X. You have a more informative X. You have a data-rich database, information-rich, okay? So your X is also bigger. And in fact, that's why we hear this thing about, Facebook or whatever platform selling your personal data, okay? So it's not about selling the model, but you can't build a better model if you don't have a lot of data, okay? So anyway, so let's say we're on the same page, right? In terms of the two primary questions when it comes to data analytics. Okay. So now let's move on then. Okay. Right. Now it's good time for me to act. Can we switch? So the subject of today is machine learning, right? Subject of today is machine learning. However, share. Oops. Okay, share. Okay. 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 See that? Okay. This is actually this is very old slide. One of my oldest slide. I keep using this. I've been this for I don't know, nearly 10 years, I guess. But it's something that I want you to imprint on your mind. Okay. What is machine learning? Before I talk about what is machine learning, and in terms of technology, machine learning seems a little bit like not so up to date, not so sexy as artificial intelligence, but actually machine learning and artificial intelligence, the story of those two things are completely connected. You can't, basically they're like sisters, brother and sister, right? So it's not like machine learning is an older technology and AI is a new technology. No, nothing like that. Okay. And the story, funny enough, starts with AI. Okay, and this is really fun. Usually, I give public talks a lot, obviously, and people tend to think of AI as the latest technology. But it turns out that historically, at least, the whole thing that kicked off this whole, quantitative model building, data analytics, machine learning, the whole thing started off, believe it or not, with AI. Okay. So I'm going to give you a little bit of story. So don't have to take any note. But this is something I want you to, as an educated member of the society, of digital society, understand really how we got here. Okay. Now, I'm not going to give you a long historical introduction to this, but basically it comes down to this. You guys know Alan Turing, right? Have you seen the movie, The Imitation Games? Anybody? Raise your hand if you haven't. If you have not. Okay, go watch it. It's a brilliant movie. Has nothing to do with imitation game. Funny enough, it's about Alan Turing during the war, okay, and what he did to crack the Enigma code, okay. It's got nothing to do with imitation game, which is something that he conceptualized after the war. Okay, so the movie is about the war and a little bit after the war, but imitations game has nothing to do with the movie. It's a funny thing. Anyway, well, the point is this: in order to do this cracking, cryptographic cracking, you need a lot of computational power, right? So basically, to make a long story short, instead of doing computation by hand, where you have to, work out all the configuration, he used computers to do it, okay? Except he came before computer was what we know of as digital computer today. So in a way, you can think of him as using analog computer, computer that has like vacuum tube. You guys know what a vacuum tube is? In a very old radio, you can see, I think he uses all kinds of stuff. Anyway, long story short, even though he had the mathematics algorithm to crack the code, he still needed the computational power of the machine. Okay? So he programmed he literally created, had a team assemble this dedicated machine that does the computation he needed. Okay? So, two things you should have heard from my last sentence is, one, there's a task, something to do. Two, there's a power. In other words, yeah, same thing, but not doable by human being. You need a machine to do it. A task and power, okay? Well, after the war, knowing that computer has so much power, and Alan Turing was ahead of his time, basically, he kind of like dreamed up basically what you guys today would call artificial intelligence. The idea was that if the computer can be powerful and do calculation, which was a human task, right? After all, he was a mathematician first, in a way. So mathematics is a job for a human being. A human being cannot do it in the scale and the speed of the computer, so you need a computer to do it, human task. Well, then you flip the inquiry around. What else can machine do that is human? In fact, if you don't make a task specific and you open up the question, the task is anything a human does. Not cracking code, not solving mathematical equation, but the task is something that human tasks. Can you create a machine to do all the human tasks? And of course, the next thing is, well, wait a minute. In that case, can machine completely emulates or imitates human being, right? Not in appearance, but in the behavioral response to the task. That makes sense, right? So again, start off from computer, dedicated task, using high power computation to do human tasks of mathematics to crack the code. Now, any task, just something about human tasks, can machine powerful enough do it? Can it do it so convincingly that it appears human? Okay. Now the appearance human is not a humanoid appearance. Back then, no such thing. Appearance is conversation, right? What I mean is that if, think about it, back then people didn't have telephone call all that much. It's very expensive. So most people communicate by letters, right? Okay. So if you write letters to your girlfriend at home, you go to war, you write a letter to your fiance at home and she writes back and, 3 months later, you get it. You're convinced you're talking to your girlfriend, right? Again, your girlfriend or your fiance get letters from you. She's completely convinced that you are still alive by the letter that you wrote, right? You're in war. So that's all the appearance you need. So the imitation game after war, once again, is that what if you can write letters back and forth between you and a machine, and a machine gives you the right words, makes you think. Now, back then, the task was not to convince you that you're talking to your boyfriend or girlfriend. The task is to say, you're talking to a human being. That's all. Okay? So the idea is A, artificial, because it's not human. In this case, all that artificial means is that it's creation. It's artificial. It's not real. It's not a real thing. It's not real thing, but it behaves like a real thing. And that real thing is intelligent conversation. Okay? So hence artificial intelligence. Now, keep in mind that word intelligence doesn't have to be intelligent. If the computer can carry on convincing conversation like a 5-year-old, right? You wouldn't go to your 5-year-old to ask for investment advice or career planning, right? Because you wouldn't get an intelligent answer from your 5-year-old. Okay, so intelligent in this case just means intelligent as if you were an intelligent animal. But human beings are supposed to be intelligent animals. So that's it. That's it. Okay. So that's the story part of it. Yeah, that's the story part of it. Now, okay, we got task. Okay. Use my hand. We got task. We got computational power, right? That task is not just computing a mathematical equation. It's a general task. So it has to be able to do many tasks. The first step to that, before you get to AI, is that back then computers were not programmable, right? It was a calculator. It does what it's supposed to do. That's it. You can't ask it to do anything it's not designed to do. So the first thing to do to generalize the task is to say, well, the task is general computation. If you know how to add, you know how to subtract, you know how to multiply, can we string together a sequence of operation so it does something interesting, right? So in other words, 5x plus 7y is a task. It requires 5 multiplied by x and then add 7 multiplied by y. But that task, once you can program it, you can also program 7x divide by 5y, whatever, something more complicated. Okay, different kind of computation. And you don't have to sort of like rebuild the machine. So it becomes programmable. Okay, so first thing of computation as something more powerful, calculation, right? Doesn't make a mistake because it's not human. So it doesn't make a mistake. It makes accurate calculation, powerful calculation, very fast calculation, but the task is what it's designed for. So now we move to programmable computer. So it can be programmed to do addition tasks, accounting tasks, finance calculation tasks, calculating the mortgage for a house loan or something like that, can do all kinds of tasks. So programmable computer. Okay. So after the war, again, 2 things happened. One is computer became programmable. I'm making the story sort of like brief, but the story is a bit more complex than that. But let's say after World War II, computer became programmable. After a war, Alan Turing asked whether computer can imitate human being. Put this and that together, then what do you get? If you want the computer to do a general human task, you have to program computer to do human thing, right? You have to program computer You can't build computer and then expect it to behave like a human. You have to program it to be able to behave like a human. Question: how do you program human behavior? Okay. Well, if you know how to program, you know how to do if then, right? Yeah, you know how to do if then. So the first answer would be, how about this, guys? How about we program computer to do a whole bunch of if then? If the input is hello, then the response is, how are you? Right? If the input is, what is 1 plus 2? Then the answer is 3. Okay? If the question is, I feel sad, then the reply is, don't be. How can I cheer you up? Okay? So you can imagine that this is an if then, right? Now, anybody see what's wrong with this? Yeah, this program would be infinitely long, right? Okay, so the only way this thing would work would be in a very restrictive thing. That's why earliest version of chatbot is only used for, anybody know? Well, not chatbot, but automated response telephone routing, right? Hello, would you like to A, B, C, D? And so it's very limited, right? It's not a real conversation. And in fact, telephone automated answer machine, nobody convinces you it's a human being, okay? But you can see that you can program that, no problem at all, right? If the question is, can I look up my appointment? The response is, give me your patient identification code or something like that, right? So all this kind of chatbot. Or the other thing is screening, COVID screening, right? You guys remember that when you go to, they have questionnaire, can you smell, can you taste, have you traveled to this country in the past 4 or 5 years, right? Well, that thing can be handled with this kind of if then. If cannot smell and been to China or whatever, right? Then better quarantine this guy or something, okay? So this kind of if then, yeah, it's a conversation, it's a dialogue, but it's so limited. So that's not going to work, okay? So once again, computers are powerful, computers are programmable, computer does human tasks. Can we program computer to do general human tasks? And if so, can we do it in such a way that you can't tell computer from human being? And how do you test that? You ask the computer to imitate human conversation, hence imitation game. Okay? Now, in honor of Turing, we now call it Turing test. Okay? We can't call it Turing test. Okay. And once again, a Turing test is considered a test for artificial intelligence, but intelligent in the sense of human-like, not intelligent in the sense of clever, right? And that's supposed to be a proof of AI. That's proof of AI. Okay. But anyway, back to where I'm heading. Where I'm heading is machine learning. Okay. So you want to program computer to if then. You can't do that. Okay. You can still do it with very limited context, like medical screening and diagnostic, a very simple diagnostic for like common cold, COVID or something. Okay. But something more advanced, you probably can't do that. Fine. If computers are powerful, we don't take that, we take that for granted. We want it to behave like human being. The only way we can do that is to program it. But we can program it infinitely long if then. Okay? Now, this is where machine learning comes. You don't program it to have if then response. You program it with a template for if then. But if then depends on some parameter set. And that parameter set can only be found by looking at real world conversation. Okay, so if I skip everything from Alan Turing, which is 1950s, all the way up to ChatGPT, can you guys see the direct line? Can you see the direct line? You can't program a chatbot or ChatGPT with if then, if then, if then. What do? You program chatbot, in this case, it's called GPT engine, with the way to look at the data. And that data is human conversation. And it learns to absorb that kind of mapping. If this is input, that should be your output. If this is input, that should be your output. So in fact, this timeline leads directly from Alan Turing to ChatGPT. The question is, what is the machine learning algorithm to do it? That's what took 50 years. Okay? 70 years. Okay? Does that make sense? So the idea is, you want artificial intelligence, you cannot program it. You cannot hard code input-output response. You can only program it with the ability to learn input-output mapping. Let me say that again. And that's the whole point of all this long narration that I'm giving you. You cannot program a computer with an appropriate input-output behavior. You can only program the computer with an algorithm to learn from example of input-output. In this case, the input-output is human conversation. Okay? So machine learning start off as programming artificial intelligence. Okay? That's the only way you can program artificial intelligence. Which means that unlike programming an accounting calculation, when you program like a program to calculate accounting or finance, right? You're programming the function, okay? You want it to calculate mortgage rate. You want it to calculate the amortization schedule for a factory, okay? That's the function. In this case, you are not programming the computer to perform a function. You program the computer to perform learning. And it's only when it has learned will it be of any use. Does that make sense? Does that make sense? If I want a computer to compute ax plus b squared minus 7 minus yx log z, okay? I just program it, right? Right? And then I want to compute it. I just put in the values and it compute for me. End of story. It does its job. I program it to do a job. With artificial intelligence, I don't program a chatbot to do a job. I program a chatbot to learn to do a job. It's only once it has learned, it can do a job. So in other words, there's this two-stage process here, right? Okay. Take a deep breath. What else has a two-stage process? You guys. Okay? You guys. Right? The education sort of like teach you ability to learn, to do things, to function. But this is not a technical school. I'm not giving you an actual, I'm not teaching you how to I don't know, fry an egg. Okay? That would be a technical school, right? The whole thing of the university is teaching you to be an educated person. Then you can go on and learn how to be a management consultant, be a marketing, be a this, be a that. And this is something that, you know, I cannot tell you. Okay. So you have to go out in the real world and learn from the problem. Okay. So when I tell you how to do linear regression, you don't even know what regression problem you're going to do, right? You know how to do regression. You go to the real world, take the real world data, build a regression model on that, right? So I'm not teaching you how to do linear regression on one problem. I'm teaching you how to do linear regression, any problem. Okay. Likewise, I'm not teaching a computer to give an answer to hello, how are you? I'm teaching the computer to learn from human being so that whatever question is prompted to you, it knows how to answer. You know how to, you know, learn it, produce the answer. So there's a two-stage thing. You program the computer to learn, and once it's learned, then it does something useful. Okay. Now, of course, just because you produce a student, you can learn, and if you don't go to work, right? You finish college and you stay at home, you don't do anything useful. That would be like training, using a machine learning to train an AI and then not use it. That's fine. The whole point is that you can't use it without training it first. So training comes first. Same thing with human being. Training comes first, right? Except in human being, we don't use the word training, we use the word learning. Okay. So anyway, so machine learning built this thing. Having said that, now this is where we get to be more interested. You will get, a lot of people will get this wrong. Machine learning is a subset of artificial intelligence. Anybody say that, you say right away, that's not correct. Because machine learning has gone on to build a whole bunch of things that has nothing to do with imitating human being. It's this kind of modality where in order for a computer program to do something, you program it with the ability to learn from data. Okay. Now that computer program doesn't have to be human-like. It has nothing to do with AI. And that's why, machine learning is like a whole career in itself. Okay. So machine learning is not just for AI, but you can say that, yeah, originally it's motivated from AI, but it went on to build a whole bunch of models. Okay. Models that doesn't look anything like artificial intelligence, doesn't look anything like chatbot. So you get a whole bunch of quantitative models as a result. Okay. And we learn some of that. For example, decision tree and that kind of thing. Once we have this, then it's sort of like chicken and egg thing. If you have a model that builds on data, right? And remember, I told you that a better model, not only is it better, it also look at the right set of data. So what happened? What happened? Okay, imagine if you want to predict Y with X1 and you're not doing a good job, right? And then a better model is to predict Y given X1 and X2, right? Okay. And your database only has X1, okay? What do? You start collecting X2, right? So it becomes this virtuous loop where the better model you build, the more data hungry it gets, the more your organization invests in data. Okay. So this becomes sort of like a virtuous loop. Okay. Where model gets data hungry, people start keeping data. They used to throw data away. Now they think data is good. So it gets to the point where even before the model asks for data, people are keeping data anyway, just in case. And this is literally, this sounds silly, right? This is not silly. That's the whole thing about all this data mining, this thing about you becoming basically fed by algorithm and all that. They try to get information about you. People who harvest data about you, they haven't built a model yet. In fact, chances are they're not the one building the model on you. They are the ones selling the data about you to somebody else who can. Okay, that's how you monetize from data. Okay, so again, let me say that again. You have F to predict Y given X1. It's not as good as if you had X2, but you don't have X2. So what do? You start collecting X2. Well, then you realize, hey, if X2 is good, how about X3, 4, 5? Now everything that gets into a digital database gets kept and maybe packaged and sold to somebody, okay? So quantitative models that gets data hungry, we use the word data hungry, right? Drives the whole world of data. And that's together, the data plus the models is where we are today, data analytics, okay? The whole world of data analytics cannot happen if you don't have the data and you don't have the model that does the analytic analysis, okay? And now we get back to finally, and this is this loop is kind of like complete circle. So the whole data analytics, the utility of data analytics is what validates the whole point of artificial intelligence to begin with. And in fact, not only that, artificial intelligence gets so smart, it starts spewing out nonsense. So now data analytics not only validates artificial intelligence in the sense that, because you start on this journey, you end up with data analytics, and data analytics is useful for business and government and everything. Not only that, but now you have to use data analytics to check on how true things are, right? And this is where it comes back to this thing about validating generative AI and whatnot. But that's beyond us. Okay, so my point is, machine learning motivated by the need to program artificial intelligence. If you cannot program if then, how do you program it? You program it with ability to learn from data. Once you have this way, this kind of two-step thinking, okay? To build a model, you just build it with a way to learn from data. Once it's learned from data, then it can do all the prediction tasks that you want it to do. Okay? Now, contrast this with linear regression. Again, linear regression is so useful to think about it. With linear regression, right? Okay. With linear regression, are you learning from data? Who says yes? Who says no? It is learning from data. It's learning from data because only by looking at past XY pair can it decide which intercept and which slope is best. Okay? It's learning from data. You can call it supervised learning if you want. The difference is this. The difference is because you only have two parameters, slope and intercept. Mathematicians have worked out a way, like a closed form formula. So you give me a pair of X and Y, I'll stick this in the mathematical formula, and I'll get the formula for the slope and the intercept. So it's learning from data, but you also have a direct formula. It's one shot. It's one shot. In other words, finding A or intercept, finding B or slope does not require iterative algorithm. Okay? Does not require iterative algorithm. Okay, now look at my hand. Imagine we have a whole bunch of data. Okay, looks like this, right? Yeah, I might as well go back to the. Okay. Right. You're right. It's learning from data. Okay. Because the best fit line is the one that is closest to all the point, right? So it learns from data. Learns from data. Fine. However, from your statistic class, you have a closed form formula. You stick in all the x and all the y. Okay. Sum of x, sum of y, x, y minus y, and all that, right? And you get that line right away. Okay. Okay. So there it is. Oops. Okay. And this is how you, all right? Oh, share screen. This. Okay. Right. This is the data, right? You're right. That blue line is drawn in reference to the points. So it's learning from data. Okay. But you have a direct formula for this. Okay. Now, let's go back to artificial intelligence. Artificial intelligence, you cannot program if and then right away. This, you seem to be able to do that, right? You seem to be able to do that because you can program this. And so when the new data set comes, you just predict if I have a new X, what's Y? That's my X, right? So it's almost like I can program this, guys. I can program this. I don't need to do any kind of learning. So how can you resolve that conflict? On the one hand, it's based on data, but it doesn't have to do this kind of like iterative learning process. It just get the right answer right away. Well, I'm gonna imagine, what if we have a dumb regression equation? A dumb regression equation is the one that starts out like this. Completely flat, zero slope, zero intercept, dumb. Or start out random. And then slowly look at the data and keep moving. Okay? Then you can think of linear regression as a learning algorithm, right? It's moving. Does that make sense? There's a process of learning from data. Now, why do I make a big fuss of this? After all, in linear regression, you already have a closed form formula. Why would you need to do this kind of like start with a dumb thing and move slowly? Because here you only have two parameters, intercept and slope. So you have a closed form solution. Okay? You know, what if you have something like this, but instead of two things to estimate, slope and intercept, these are called parameter, right, of the function. Instead of having two parameter, you have 175 billion parameter. That's what ChatGPT 3.5 has, right? That's why it's it can't do this thing that linear regression does. It doesn't have a closed form solution for 175 billion parameter. So it has to have a way of moving the 175 billion parameter. And I haven't even told you what it looks like yet. Think of it as a gigantic equation. Okay. At the end of the day, it is a mathematical equation. It has 175 billion coefficient. That's what GPT 3.5 is. it's a function with 175 billion parameters. So that's why it can't do this thing in one go. And how does it do it? Well, instead of having X and Y, you have human conversation. So the story is right now seems to you like an analogy, but promise you, that's exactly what's happening. What happened? Okay. So let me say that again. You are trying to fit something to the data, right? But you can't do it one shot. So this if then doesn't work. It's one shot. Doesn't work because human information is infinite. Likewise, this closed form formula, there is a closed form formula for the slope intercept, doesn't work for a regression equation with 175 billion parameters. Okay, so think of GPT 3.5 as a quote unquote regression line with 175 billion parameters. You know who else has that many parameters? You. You have trillions of parameters in your head. Okay, the connection strength between neuron. Okay, so basically, if you look at the okay, your brain has about 85 billion of this guy. Okay, this guy takes a signal from this guy, multiplied by something, and then send it to other guy. Well, if you have 85 billion of those guys, you have trillions of connection. And each connection has some kind of, think of it as a weight. The weight is your brain's parameter. And you have trillions of them. So your brain is much larger than GPT 3.5. Okay? Your brain is much larger than GPT 3.5. The reason GPT, well, I won't go into that right now. Okay? So basically you have a bunch of these. So let me summarize what I said. Okay. So AI, okay, if, then doesn't work. If then doesn't work. If then doesn't work. What else doesn't work? This closed form, okay? For example, beta estimate is equal to sum x, y, that's a formula. This thing also doesn't work, okay? This thing doesn't work, 475 billion parameter. This thing doesn't work again because human being has gazillion infinite conversation. So you have to have machine learning. And let me write this in a big algorithm. Yeah. So when you said earlier, it's linear regression, the machine learning, it's like learning from data. Yes, but it's not an algorithm because it gets there in one shot, right? You need this. This algorithm, okay, this is the action. Okay. The algorithm does this. I have F with this, okay? And this is about, say, 175 billion, okay? Lots of them, okay? Now, okay? But right now, it's completely random, okay? Starting, okay? Starting. Go to this algorithm, machine learning algorithm, okay? And this thing requires a whole bunch of X and Y. Okay, watch this, okay? Now this is very important, okay? You put two things together. You put the model, like regression line, with a placeholder for the parameters. Start with 0, let's say, okay? In real life, doesn't start with 0, start with random, but never mind. Think of it as start with 0. Then you put in data. So this is data. This is model, okay? But that model is not calibrated because you don't know what this is. You put in the machine learning algorithm and you spin it 1,000 times, 1,000,000 times. And this is where you said you can't do it in one shot. You have to sort of like keep moving the parameters slowly. And then you get F star such that this F star F of X given theta, okay, I didn't put rule, is equal to Y. And this Y is close to that Y. Okay? You don't have to write this down because, you know, this is a bit messy. Okay. So let me say that again. You can't program an AI to have behavioral response like a human being because that would take infinitely long if then. You can't program an AI to do prediction the way linear regression does because you have gazillion parameters. Okay? There's actually more mathematically precise reason for that, but basically you just have too many coefficients. So somehow you have to start with a function that looks like an empty brain or linear regression, but not linear and 175 billion parameter, and then show it the data and have some kind of algorithm that keeps moving the coefficient so that at the end, the parameter you train will allow you to make very good prediction. Okay? Right? So you put in, now, I'm going to give you the terminology. This thing is called machine learning, but they don't use the word learn when it comes to model. They use the word train. So this thing is untrained. This thing is trained. Okay, so I'm going to start a new cleaner slide. Okay. Okay. Untrained model is equal to f x given theta. So this is input variable, and this is function, yeah, parameter. Okay, that's it, right? But when I write it like this, it's just a placeholder. It's just a placeholder. Okay, it's like y is equal to ax plus bx squared plus 3 plus cx cubed. Okay, it's a placeholder for x. It's a placeholder for coefficient, right? It's just a bare bone mathematics. That's what untrained model is. The data is actual x and y. Now, I can put in some index to say that, you know, number of data point. So maybe you have 1,000 point, okay? And then a trained model is f of x given theta star such that y hat is close to y for every pair. Does that make sense? Now go back to your linear regression. That's what linear regression achieves, except linear regression, because there's only two coefficients, it's done in one step. I give you a bunch of X, I give you a bunch of Y, right? And then linear regression, say Y is equal to A plus BX. Okay, put in a bunch of X, put in a bunch of Y, I get Y, and I get AX plus A plus BX, and then A is equal to some number, B is equal to some number. Okay, but this structure is what we're going to have to do, because again, number one, it's not an if then. Number two, it's not that simple linear regression with two coefficients. It's 175, once you get to 1,000 parameter, you definitely can't do it. So that's where this thing and this thing go to a machine learning algorithm, give that. So a machine learning algorithm is what? Okay, think of an input. What do you need to, think of a program. A program say machine learning. What do you have to specify in that program? Number one, what is the model? What's the F, right? And that F has a placeholder for the parameters, right? And based on that F, based on that coefficient or parameter, it gives a guess for a Y for whatever X you give it. So at first, you give it all the X, it's going to give you all the Y, but it's going to be silly. It's going to be far away from the truth, right? So it's going to be inaccurate. The machine learning algorithm is a loop that keep adjusting this guy, so that goes from theta 0 to theta 1 to theta 2 to. That's what a machine learning does. Okay. Now this is, so far what I've been saying is a little bit intellectually challenging, but you have to think back of, this is how AI has evolved over the past 50, 30, 70 years to where we are today. And it's an amazing technology. Okay. Now, this is the what we need to do. What's machine learning? Machine learning is an algorithm, is a program, iterative steps, step, that move the parameter of the model so that it can make good prediction. And what do I mean by good prediction? Because if I give you the past example, it matches the previous example. If the previous example is X, the previous Y, and you give it the previous X, and the model gives the Y that's close to the Y in the data, then it's good, right? Okay, now. Okay. I want you to think back to when you were young. Okay? When you were young. Again, AI in a way is an analogy of you, right? So this is your brain. What do you have to do to be a functioning adult? You have to learn, right? You have to learn. And what does learning do to you? Does learning create new neurons? Some medical research say maybe, but on the whole, no. On the whole, no. What learning does to your brain is to strengthen and weaken connection. Some connections are strengthened, so that's like give up, and some connections are weakened and disappear altogether. Okay. In fact, this is actually real science, guys. You were born with a lot more connection than you have now. And as you learn, connections that are not used disappear. Okay. So it's as if It's like this. It's like this. With linear regression, you have two parameters, right? With ChatGPT or GPT 3.5, you have 175 billion. Your brain, and don't quote me on the number, I'm probably wrong on this, but let's say your brain has 5 trillion parameters. And those parameters have to be tuned. In fact, by the time the model tuned, a lot of them will disappear altogether. That's like saying that the value is equal to 0. Would you agree? Right? So when the value of the connection is 0, it's not positive, it's negative, it's 0. It's the same thing as your brain pruning. And that's what your brain does. You know, when you were born, you have more connection than you have now. And your brain, some of the connection that you don't use, you lose. Some of the connection that you use more become stronger. Okay. So, you know, when people say, you know, if you don't use your brain, you lose it. Literally, that's true. You're not losing the neurons, you're losing the connections. Okay. Now, some of it is because you don't want, you know, you want to have the right parameter. But anyway, so my question is, you have to learn. Who else has to learn? Artificial intelligence has to learn. Okay. So now, after Alan Turing, let's say move 10, 20 years. If you can't program and you want to do what the challenge that Alan Turing set out for you, which is to train an artificial program to behave like a human being, you have to create machine learning algorithm to do that. My question is, what would such a program look like? Okay. You guys know what an algorithm is, right? First of all, an algorithm is a description of procedure that's done in steps, right? That has a basically beginning, middle, and end, and there's some kind of looping. It's like well, a good way. This is not just mine, but everybody say this. Good way to think of an algorithm is to think of it as cooking, right? A cooking tells you the step. Cooking recipe tell you the step. Take the egg out, beat it. Now, if you notice, when you beat an egg, you don't do it once. So what does the algorithm for beating an egg look like? Stir until blended. So there's an iterations loop right there, right? And there's actually a check because you don't beat it forever and you don't beat it for 1 second, or, you know, some algorithms say beat an egg for 5 minutes. Okay, that's one way of doing it. The other algorithms say beat an egg until the egg yolk and egg white completely blend. Well, that's a do while loop, right? Do while, if, then, for. These are all algorithms in a computer, but you're doing it with a human being, right? So an algorithm is like a cooking step. Except the step here, you start from egg white and egg yolk that's not blended. You end up with egg white and egg yolk that's blended. Then heat it up. Again, heat it up. You also have a recipe. Heat up for 5 minutes or heat up until golden brown, right? So when it's golden brown, you stop. Likewise, the cooking here is you start with 175 billion parameter. It's completely random. You move it until you get to where you want it. And where you want it is ChatGPT, that's, you know, or GPT 3.5 that's released in December 2023. Okay? Now, cooking an egg takes 5 minutes, 10 minutes. ChatGPT or GPT engine itself took the most advanced, most expensive computational setup, you know, human being has ever known almost, and ran it for like 8 months. I don't know how many months. Okay, but months, not or weeks at least. I'm not quite sure, but certainly not 5 minutes. Okay, so yeah, they have to have that. My question is, what does machine learning look like? And this is where it gets where we are today. What does machine learning look like? machine learning algorithm. What does it do? Sorry? Adjust? Yes. Well, if the model is neural network, yes. So in fact, I have to say this. So this is you, and then you have like an empty space, like trillions of space, okay? And you have a neural network, and you have a lot of space. You have GPT, you have this. You also have something that has nothing to do with artificial intelligence, like decision tree, right? You have all this, okay? So again, all this is your theta 0, theta 0, theta 0, okay? Different size, right? Same thing as, if you think of linear regression, you can also think of it as A and B, A0, B0, right? So you're kind of moving this until you get the final value. Once you get to final value, it's frozen. Okay? ChatGPT does not change its learning. When they say that ChatGPT learns from you, technically that's not correct. ChatGPT doesn't learn from you. ChatGPT has finished learning. When they say ChatGPT learns from you, it simply adds more background about you to make better prediction. Okay, but ChatGPT's parameter is 175 billion set of number. They're not going to change it just because you ask the question, right? So it's frozen. So the idea is you get this to there. Well, and this is where we get to this thing called machine learning paradigm. Okay, paradigms. Paradigm means, well, you want the machine to learn. I just described the task for you, right? How? How? Paradigm is not only how, it's a how with an example. Okay, it's kind of like, this is a paradigm of virtue. That means this is an example of virtue to look up to. You know who the artificial intelligence look up to as its paradigm for learning? Children. So in order for artificial intelligence to learn, it mimics what children do. Now, how do children learn? That becomes. Now, my hint, I put an S. So there isn't one way. In fact, there are three main ways children learn. Okay, when we finish this, we'll take a break. Okay. Okay. Or you want to take a break now? Huh? Let's go. Good. Okay. How do children learn? Think back when you were a baby. You just came out of your mom's belly. Okay. You can smell things, you get hungry, blah, blah, blah. You can look around. Let's say your eyes start to open. Okay. You learn about your environment from observation. And you sort of like build an internal model of how the world works. By which I mean, if every time you cry or every time your mom comes by, you have a nice smell and then you get fed, you kind of automatically associate your mom with happy, right? So you don't have to be taught anything, okay? Nobody teaches you anything, but by the fact that when you're hungry, your mom comes in and you get milk and stuff like that. So it's kind of nice. This thing is completely automatic. You learn on your own. And you start to associate on your own. Your mom, nice smell, get fed, okay? Maybe a baby brother is noisy, whatever, okay? So this thing is completely unsupervised. So this is called unsupervised learning. Okay, unsupervised learning. So I can put M over here, unsupervised machine learning, or I can just say unsupervised learning. Okay, I haven't shown you how yet. Now, of course, the bulk of your growing up, you are taught, right? You're taught. Now, this is where you get taught. What is teaching, guys? What does your mom do when she teaches you? She shows you the right pairing. The pairing of this thing with the word pen. Pairing of this thing with the word water. Pairing of this thing with orange. Pairing of this thing with bananas. Okay? Shows you this. Okay? Shows you if you see this fruit, say banana. If you see this fruit, say orange. Okay? That's not finished yet. That's not finished yet. That's just showing you, right? How does your mom teach you? Get you to say. And if she shows you a banana and you say banana, what does your mom do? Good job. If she shows you banana and you say orange, she say, no, 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 no. Right? So immediately she gives X, Y pair. Not only does she give you X, Y pair, she asks you to say Y for a given X. Not only that, she gives you immediately feedback whether or not your Y is the right Y. Okay, 3 things, right? Show you, get you to do the X to Y, see X, call Y, see X, call Y, see X, call Y, right? See this fruit, say banana, fine. And then feedback, immediate feedback. This process is very intensive. In fact, that's why human beings are more advanced than cephalopod, like, octopus. Octopus are very smart, right? Anybody knows that? Yeah. The reason they're not that smart is because they don't learn from their parents. In fact, their parents, leave. In fact, die, right? So they don't learn from their parents. And the reason human beings are so smart, and the reason why you guys are useless until you are adults, is because instead of animals do this, guys, they drop out their mother's womb and they become functional. Human beings do not become functional. And for the 20 years that you are not functional, that buys you time to learn in a supervised mode. Okay? Animals don't have supervised mode. Not very much. Chimpanzee does, maybe. Okay? Primates and mammals do, but certainly reptiles don't. Okay? Reptiles don't learn from they can observe. So they do unsupervised learning. Okay? But you don't see mother crocodile say, okay, this is good. Eat buffalo. Don't eat vegetable or something like that. You don't see that, right? So this thing is called supervised learning because your mom has to supervise you. Okay? It's not enough to show you, right? That's a passive thing you can, but you have to say apple or banana, and your mom will tell you right away. Okay? So direct feedback. So this thing is called unsupervised and supervised machine learning. Supervised. Okay? What else? Well, actually, it turns out there's another 1 or 2 paradigm of learning. You go to kindergarten. If you behave well, okay, you don't bully your friends, you share your toys, kids like you. If you go in and you don't share your toys, you don't, you steal your friend's lunch, right? Your teachers haven't seen that. They didn't notice that. But you know who's going to notice? All your friends. What happened? Over time, you know what's the right behavior to navigate the social network, right? So you get feedback, but is it direct feedback like your mom? So if you push your friend and your mom say, no, Johnny, don't do that. That's bad. That's supervised learning, right? But if you push around your friends and after a few weeks, no kids want to play with you. right? This is kind of like long-term evaluation, okay? So it's kind of like, it's not direct, it's behavioral, it's a long-term, and the behavior, the point is that good behavior gets reinforced positively. Bad behavior get reinforced negatively, meaning, you know, downplay. So this is called reinforcement learning. Okay, reinforcement learning. Now, this is called UL, SL, and RL. These are paradigms because the example is human. So this brings us back all the way to Alan Turing. Alan Turing challenges you, say, can we get a computer to behave like a human, at least conversationally? Computer scientists in the subsequent year realized they can't program it directly, so had to come up with machine learning algorithm. And where would you find inspiration for machine learning? You look at baby learning, children learning. That's why it's called machine learning paradigms. Okay, paradigms are like example you follow. Good things. Okay, so if AI wants to behave like human, and you can program it if then, you can put in a closed form formula like regression equation. You have to slowly move the parameter all 175 billions. You're going to have to do it, but how? You look to human for inspiration. After all, that's what you're trying to get to, right? So these are the three ways that we create. So if you look up, say, a code base, you go to like GitHub, okay? All this code base, machine learning algorithm, roughly speaking, they will be organized or categorized into supervised learning algorithm, unsupervised learning algorithm, and reinforcement learning algorithm. Okay, now I'm gonna let you for a quick break.